Well, first of all, I would like to thank the organizing committee for inviting me to give this talk. I'm going to change a bit the focus of what we have been listening so far today. I'm going to change a bit to biology, but in terms of micro systems, or what we call proteins. And proteins is the love of my life in my academic career. So I'm going to talk about proteins and how it's important to understand the structure of these proteins and what methodology can we use combined with computational biology to get insights onto the structure of membrane proteins in particular. So I want to focus a bit on the title because the title is a bit long. So basically the title is mentioning three important points of my talk. Mass spectrometry, which is a technique that I'm pretty sure that everybody, including this room, have used. In particular, when we travel overseas, in the US or in the Europe, usually sometimes this immigration officer pick up like a pen and a brush and touch your clothes or your backpack, and then put this sample into a machine, a small machine, and say, okay, you are free to go or not. You got some TNT or some other explosive in your clothes. And this explosive is basically detected by mass spectrometry. So I want to tell a bit about this technique. In silico collision-induced dissociation, a long name, and this name represents the basics of the detection of this instrument and how this methodology can be used to understand proteins. And finally, what I suppose everybody have heard, molecular dynamics simulations in order to get membrane proteins in particular moving and getting interesting insights onto the structure. So first, membrane proteins. Membrane proteins are basically proteins that live happily in the membrane of all of our cells. So our cells is like I'm getting a picture, very basic picture, like a sphere. And this sphere is surrounded, the same cell is surrounded by the plasma membrane. And this membrane separates the extracellular medium with the intracellular medium. So if that's the role of the membrane, for example, you can get a lot of water outside and the cell doesn't collapse or inflate. And the reason why is a lot of physical chemistry behind. And in particular, there is a role of proteins. And these proteins, which are inserted in this plasma membrane, can fulfill a lot of functions. They can recognize signals from outside, synapses that we got all of in our neuroscience, neurological system. So they got communication between cells. So these membrane proteins are really important to get these connections to work. We got also proteins that are important for nutrition, food. We got proteins in food. But proteins that are inserted in plasma membrane, they got a physical chemistry rules that are different to most of the proteins. And these rules are, I live happily here, but I got to be a connection with the lipids. This is the lipid, and the extracellular and intracellular medium. And the mediums are different. So the extracellular is water, inside is water, but the membrane is like a fat. So you can imagine a drop of water and a drop of oil doesn't mix together. So this protein got advantage to get to touch and to live happily between these two environments. Because of that, the structure of membrane protein is difficult, pretty difficult to get. So what the researchers have done is remove the protein from the membrane and get the protein isolated, I would say alive, and almost native, like in the membrane, but it's surrounded by this ring here. This is a cut, a transversal cut of these sexes, and these things in here are detergent molecules, the same like detergent we use for we wash ourselves, or the plates or dirty dishes. This detergent keep the protein alive, And this sample is the sample that we use to get a structure of that. How many residues got the protein? How big is it? How many subunits or how many proteins are in the same protein, etc. Okay, so there are several methods to understand the structure of proteins, from the highest resolution to the lowest resolution. Highest resolution means that, for example, if all of us represent a residue or amino acid, and all of us represent one single protein, it's important to me to see where is that residue, the guy with the glasses over there. Is it sit there, or in the middle, or in the left hand side? That's really important for the function. So I need to know where he sits. With these techniques, I can get the specific residue and the position in the space. Unfortunately, for membrane proteins, crystallography and NMR are really difficult because the sample, you need to get a lot of sample, and experimentally it's really expensive. So if you are successful, after a couple of years, you can get a nice paper. If you are successful but a bit slower, after 6 or 5 years, you can get a nice paper. And if you are unsuccessful, you can work 20 years, you don't want anything. So it's really a hard task to use these technologies. So for the researchers in biology, they said, okay, we need to complement these techniques with low resolution techniques, but still they work. And these are a number of techniques. We are going to focus today on this particular mass spectrometry technique. And as any spectrometry technique, the result is spectrum. So you get a spectrum. And spectrum, you have to interpret that spectrum in order to get information. And mass spectrometry, the information is mass. Okay? So this is the number of structures, protein structures so far. You can see that the number is increasing quite dramatically, over 100,000 structures so far. But out of 100,000 structures of protein structures, most of them are soluble proteins. Remember that membrane proteins are just in the membrane. So most of the structures are coming from soluble proteins, that they float inside the cytoplasm or inside the cells or outside the cell. But only a small percentage of proteins is becoming from membrane proteins. So it means that we need to get more techniques to get an increase of these structures. Okay, let's talk about mass spectrometry a bit. Mass spectrometry is a technique, as I said, is very useful for us to travel overseas. I mean, in a safely way. This is a kind of mass spectrometry. This in here, it represents a glass, a pipette glass. Inside the glass, there is a solution or a buffer containing the sample. In this case, the protein. So the protein is electrospray into the instrument. There is a lot of physics behind hard physics about collision events and desolvation processes. So the protein is in water. So you have to remove the water, and then the protein is naked. And protein naked enter the instrument. When the protein enters the instrument, the protein gets charged. And that's the key thing for mass spectrometry, for all the mass spectrometry techniques. The protein has to be charged. When the protein is charged, positively charged, then you can use a lot of components in the instrument to guide the charge. Because a protein is charged, you can use different voltages or guides, and these guides can actually place the ion where you want it and move the ion inside the instrument, and finally be detected. And what's detected is this spectrum. And so in a few words, this spectrum means different charge states. So any protein got different charge state when it's charged in the gas phase. But there is an average. So this is 21 plus, so 21 protons inside the protein, 22, 23, until 25. This is like a Gaussian distribution, So the peak represents the average charge state. And this is proportional to the size. So if after you got the result, you got the charge state, and you got m over z. So the z is the charge. You can actually get the m, which is the mass. So with this sort of a spectrum, you can get the important thing for us, the mass. Let's go back to membrane proteins. So membrane proteins are heavier than soluble proteins. Why? This is a membrane protein. Just imagine this protein inside the plasma membrane, but when you remove that protein to get it to work with any other methodology, this protein is covered by this ring, the detergent ring. So the molecular mass of this is bigger than this, right? Because the red thing is getting the protein heavier. So this mass is heavier than this. But we don't care about the detergent. We don't want to get information about the detergent. We want to get information about the protein. So how can we get information about the protein? So this is about 2 years ago when we start this project. This is a model, Olato model of a membrane protein. This is the membrane protein. These are detergent, and these white things, small spots, are gas molecules. So these gas molecules are inside the instrument. So this protein in here is actually going to move from here to outside the panel, and when it moves, can you see that it's colliding with these gas molecules? So when the number of collisions is increased, what we expect at the end is all the detergent is removed. And when you remove all the detergent, you get the naked protein. And if you get the naked protein, you get the information about the mass. That's the idea of the experiment. So first of all, we need an instrument to be able to collide gas molecules with the protein. And second of all, we have to control this stuff in a really tunily precise way, which is not at all easy. What we see from the experiment is this is at low number of collisions. We don't see any signal. Remember, a spectrum is information for us. And here we see like a hump or a mountain. When we increase the number of collisions, we start to see peaks. Until here, we see maximum energy in the instrument or whatever, and we see peaks. And when we see peaks, we got the information about the molecular weight of the protein. And that's the information for us. Remember crystallography, that we got the position of every residue in the space? In here, we cannot get that information. But at least we can get the mass, which is really difficult for membrane proteins, the overall mass. And mass spectrometry, because it's so sensitive, we can get the precise mass, even the mass within the error of 1 proton. It is really high resolution. What we have understood so far, this is the energy required for soluble proteins. This is the energy required for membrane proteins. So we need a lot of collisions to get information about membrane proteins. Yes?
So the mass gives you information on the structure.
Say again, the mass don't give information about the structures? Yes and no. Yes, in terms of if the protein is one single peptide, polypeptide. If you understand, a protein is a polymer composed by many residues. So if all of us are residues and we are single protein, this is going to give you the molecular weight of one single protein. I wouldn't say structure of that, but just imagine different rooms. This room, the other. We don't have any information about the rooms and the number of people, but we got the overall molecular weight. That's a bit more abstract because we don't know what the number of people, and we can get the overall mass. From that point of view, it's a structure. And I'm going to show you later about other things that we can get from mass spectrometry. Okay, so but from that point of view, it's a structure. It's depending upon the information you get from the instrument. Oh, sorry. Okay, so let's combine a bit information. Why it's used for mass spectrometry? It's a really expensive technique. So let's see here. This is data from a microscope called AFM. This is the AFM. It's a tip, a metal that is touching the surface. Basically, it does a lot of things. But for us, the only thing it's doing for this talk is touching the surface. So I got this pointer. I'm touching the surface, getting the surface, the surface of the sample, and I can see 2 spots. These 2 spots means for us, okay, this protein could be double, right? or two of the same. So, but nothing more about it. So it's like a double, but no more information about it. So when we use the same sample and we run mass spectrometry, this is a spectrum, and we can get actually the peaks, a lot of peaks. But these peaks, the 28, 27, and go on here, gives you the molecular weight of MACB, which is a protein, and it's dimer. So in biology, when we got two of the same kind, it's dimer, three of the same kind, trimer and tetramer and so on. So this is a dimer, and the molecular weight or the mass is precisely the dimer. So we got information about the dimer. Let's talk about another example before going to the hard modeling. So why is important this technique? This is a machine, a molecular machine, intracellular molecular machine. We got, everybody has got this machine. It's located in mitochondria, and it's basically it's designed to create ATP. And ATP is a small molecule, very useful for metabolism and to get energy. This is the ATP, like a fly here. So this is a model, an old model, and people wanted to know what's the number of proteins here. What's the molecular weight of this? It's unknown at that time. So we use mass spectrometry. This is what's a hypothesis. We use mass spectrometry, and we got finally a lot of spectrum. It's a bit complicated, but in here, with the star, we got the spectrum corresponding to the intact molecular weight of the ATPase, which is the protein here. So with this information, we can get, as I said before, the molecular weight of all the rooms in this hotel, and what's the mass of every of the rooms in this hotel. That's a bit of a structure here. Okay, this is for a different enzyme or different membrane protein or different molecular machine. But let's focus a bit in here. This machine, as any machine built for any company, costs a lot. But if you invest $200,000 to $300,000, additional $300,000, you can get an additional model, which is called ion mobility. And this model gives you information about, of course, not the same as crystallography, but information about the structure, about shape. How is it? So this is a collision. It is based on the concept called collision cross-section in square Armstrong. What's that? Just imagine a membrane protein here. This is the membrane protein. Is floating in this space, in this room, and you record all the shadow is below, just below that. You record all of the shadow, is an area, square Armstrong. You get the average of all of the orientation of this protein, and you can get collisional cross-section. And this is theory, right? But you can get the same collisional cross-section inside the instrument. Why? Because the instrument got this additional ion mobility model, where the bigger the ion, the longer the time to reach the wall. So if I'm a small ion, I'm gonna take 2 seconds to reach the wall. If I'm a really big ion, I'm gonna take an hour to get the wall. So that relationship gives you in the instrument collisional cross-section. So I can combine theory with experiments here. So why it's important? Again, go back to the synthase, which is this big protein. You know what? When we got a pump, a pump to move something, where you have to apply energy from this position, from this table to over here. So we need to apply energy to move the water from here to here. We use a pump, and this pump usually needs a lot of oil. In particular, when they are not electric, they need oil, and this oil is actually inserted between the how to say the part of the machine. So you need oil to get to finally tune the movement of this part of the pump. Sorry, I forgot the name of in English. Okay, so if you move to the protein, what's oil in a protein? Oil, remember this oil is lipids? Lipids are oil for us. So in here, this is a part of the protein. This red thing is a protein, but this green thing is lipid. for us, oil. So there is a lot of biology behind that, but the important thing here is, can you see the green thing is inside this protein? It's in the center of the protein. What's the role of this oil, of this lipid? Is regulate the velocity of this protein or enzyme. So the bigger the hole, the difference in terms of efficiency of this protein. But this information, we can get it with mass spectrometry, not other. So we can get the number of lipids inside. What are the lipids? So what's the oil? Remember, you got the car, it doesn't, I mean, if you got the car, you have to use the precise oil inside the motor, right? So you don't use a different kind of oil. You use the precise oil that the car needs. And here, this is specific for any particular protein. Remember the shadow? The shadow I show you here in this video. So this shadow, well, this shadow in terms of the experiment is this shadow here. This is the shadow. You take the shadow information, don't forget about this stuff, and you finally, with this shadow information, you can get a dimension of this structure. So you can propose a structure like this, and you use the information about the shadow, which is the shape, and fit the data into the shape. So in other words, we use mass spectrometry to get the molecular weight and also the shape and fit the model, our molecular model, into this shape. Okay, I'm gonna skip. Oh, no, I think I'm on time. So then you can mix different techniques. You can get the same structure in here. You can use microscopy to fit all the data. Remember the first slide I showed you, the second slide about different methodologies. So you mix all the methodologies and you get information about the structure. And that's the important thing for us as biologists. We need to combine methodology or theory to get the protein to work or explain how the protein works. Okay, so then we got a spectrum. We got a lot of different techniques that can be combined to know about the protein structure. But let's talk about how can we predict this? How can we characterize this behavior of this protein in the gas phase? A bit complicated picture, but here we got different membrane proteins with the rings. Remember the Dayton rings? And here we got without the rings. And in here, in this axis, we got a concept called accessible surface area. An accessible surface area is like the area which is, as the name said, accessible to a solvent. So, for example, if we are swimming, I don't swim, but if we are swimming, the water is touching ourselves, right? I mean, the head, the hair, the ear. But if we are, we got dressed like this, of course, the water is unlikely, just imagine, unlikely to touch inside this, right? So it's touching my clothes, but not inside me. So accessible surface area is like an indication of what is accessible to the surface. So if I calculate the accessible surface area of this glass with water, this is accessible, but inside the water, I cannot access without touching the water. So it's inaccessible, okay? So if I calculate the accessible surface area, which is the area that is feasible to be charged, I can get a lot of information in here. And it's a nice correlation between the charge and the accessible surface area. The bigger the charge, the bigger the accessible surface area. And that makes sense. The bigger the protein, the bigger the charge the protein has. Okay, so then we pick up examples that we got experiment for that. We got a transporter, it's a membrane protein, a potassium channel, another membrane protein, a small transporter, another membrane protein. We model with the detergent molecules. We make the rings. We got information about the mass spectrometry data. This is the shadow again. This is the mass spectrum. This is the shadow. And this is what is important for us. The measure and the expected CCS, the collisional cross section. In this experiment, it's really similar to the measure compared to the expected. So the theory is similar to the experiment. So in other words, the shape that the protein has in solution is similar to the shape that the protein has in gas phase. Similar, not the same. So if we got that model, we start to use molecular dynamics simulation to understand or to sort of propose how the protein behaves in gas phase. So in here, this is the starting from zero. What is zero? It's a membrane protein with detergent molecules. So this is a membrane protein, the times go on, and finally I see a formation of a membrane protein bound to detergent. How can we do that? In molecular dynamics simulation. So we do that. This is the same data, but it's like a video. It's better sometimes getting a video. So this is the membrane protein, this is the detergent are floating around, and just take about 30 seconds. After a while, the detergent is getting attracted to the hydrophobic part, to the center part of the protein. Can you see this detergent is floating around? There is water in here, you can see the water here. You cannot see the water here. And then the detergent is getting attracted to the surface in a particular way. If you wait for a little longer, then some of the detergent are getting plastered, and at the end, can you see that it's getting sort of touching the surface of the hydrophobic part of the membrane? And after a while, for us it's around 2-3 microseconds, which is a lot. Can you see clearly detergent bound in a sort of stable way to the membrane protein? And that's our material. This is our material that we are going to get into the instrument or into the gas phase. Another important point here, can you see these are like a tiny spots, green spots or pink spots? These are not residues. Why they are not residues? Why this is not all atom simulation? Because all atom simulation with our 500 cores took really long. So even with 500 core, $150,000, this is really long. So we have to move to a sort of a feasible way to do that, and we combine residues. So like all of the guys in here of this table, which are residues, are combined into one single spot. And this is one single spot in here. So it takes the simulation shorter, and this is for molecular dynamics simulation, it's called coarse grain simulation. So we use that, and we can get a simulation of the membrane protein. So then we pick up this membrane protein with myself, and we get it into the instrument inside the computer, and said computer collide this protein with gas molecules. And at the end, we see destruction of the mice. So let's see how this destruction happens in terms of numbers. CCS, remember, collision and cross-section, is increased for all the proteins. Kirvac, BTUCD, and EMRE, different proteins, different sizes. Bigger CCS for the bigger protein, as expected. This is the change of temperature. In total, it's around 20 nanoseconds in this particular simulation. This is accessible surface area, also a trend that at the higher number of collisions, a higher magnitude of accessible surface area, bigger for BTUCD and Kirvac than EMRE. So the bigger the protein, the large number of collisions you can get, or you have to get to remove the problem. So can you see this? Yes, so it's a bit quick. In the left-hand side and the right-hand side, there are different proteins. And in here, there is not molecular dynamic simulation. This is just an approximation that we call statistics, but I would say, without offense, not sort of statistics, it's like a basic rules. So I'm gonna go back again for the BTUCD in the left-hand side, just focusing here. So can you see this thing floating around? These are detergent and are jumping from the protein. And the rule to do this is not molecular dynamic simulation, it's just a simple rule. If we are a number of people in this room, and I'm coming from this side, I'm gonna touch first these guys, not the other guys. So the accessible surface area for me is bigger for these guys compared to the guys in the center. So using these basic rules and some other rules about how the collision would be, I can sort of propose the movement of this detergent. or the movement of the residues, and can combine this information in terms of energy with the molecular dynamics simulation. I'm going to show you in the final slide what does it mean. Okay, so I'm thinking, yeah, my talk is a bit short. Well, anyway, it's better. So this is the final set of slides. So now we want to the more challenging way. It's make the collisions inside the inside the computer or inside the mass spectrometry. So we have chosen again a membrane protein covered with detergent. These white things are detergent, and we are gonna put this membrane protein into a 3D program, like a program we use for 3D movies. We made some in-house scripts to use all the mechanics or nanomechanics information from this software, and we say the instrument, or sorry, the computer, we are gonna consider the mass of the gas molecules, which are not drawn in here, the mass of the residues, the mass of the detergent, and we're gonna say, okay, this membrane protein move to because of a defined kinetic velocity to the wall. But in the movement between here and there is a lot of gas molecules. So these gas molecules are going to collide with myself, which is the protein. This is the number of collisions. This is the distance between detergent from here to here. So at the low number of collisions, nothing happened actually. The distance of the detergent is the same. But suddenly, after the number of collisions is really high, the number of detergent, or the distance between the detergent, is getting increased dramatically. And when we see the structure of that point, particular point, we see that actually here, it's almost intact, but in here as well it's intact. The difference between here and here, it's basically detergent absence. So we can say from this data that we need for this membrane protein with this kind of detergent around 5,000 number of collisions to get it to work, to get it detected inside the instrument, which for other data we got is really similar to the experimental number of collisions we got in the instrument. So then we say, okay, we got a nice system. Let's play around with the system, because we got a clone of ourselves inside the computer. We can get ourselves stronger, shorter, bigger, fatter, whatever. So then we say, this is the control, or this is the control, this one, the control data. And we said, okay, I'm gonna tell this protein to move 5 times faster. So the speed is 5 times faster. And of course, if the speed is 5 times faster, the kinetic energy is getting quite high. So you need a lower number of collisions to get removed the detergent, because any collision with the gas molecule it's energetically larger. If you reduce the kinetic energy, you need more collisions to get the protein removed or to get the detergent removed. What happens if you are self? You mean I'm the protein with the detergent, you are the gas molecules, but you are fatter, bigger. So you got a more gas pressure, you need more collisions, I need more collisions to remove my detergent. What happens if the gas molecule, the mass of the gas molecule is different? The bigger the mass of the gas molecule, the shorter the number of collisions. That's because the energy is used stronger in this particular case compared to a smaller molecular weight of the gas molecule. So finally, the last slide, well, almost last slide, when we group or summarize all our data in terms of hard molecular dynamics simulation with this in situ or in situ instrument in a computer way, inside the computer, we combine the number of collisions, the temperature we apply to the system, and this distance between detergent, which is a measurement of how destroyed is the detergent or how removed is. This is molecular dynamics simulation, and this is nanomechanical simulation, which is the collision events between the membrane protein and the gas molecules. And basically the curves are similar. So for us, what does it mean? It means that we can now use our inbuilt instrument in the computer, and we start to play with any membrane protein that we want. with any combination of lipids or detergent, and we use the simulation, and we can estimate how will be the molecular dynamics behavior of that system. Taking that information into account, we can design what's the best protein in what buffer and what detergent can be used to be detected into the mass spectrometry. So in other words, we can describe now how is the behavior, sort of behavior of membrane proteins in the gas phase, and also how we can design now better experiment, less expensive experiment to get information about the structure of membrane proteins. So finally, we propose with this method a sort of a more detailed explanation about how membrane proteins behave in gas phase, which is another technique that we are now using to understand the structure. These guys in here collaborate or have done all this work that I showed today: Mario, Natalia, Felipe, Jorge, Gonzalo, and Dr. Soledad Torres has been a long-term collaborator with us, in particular in terms of the statistical approach to understand the release of detergent molecules. I hope that I made my point clear, and even though it's a bit far from what you have listened so far today, but my message, I hope my bottom line message is, in biology we use a lot of numbers, and for biologists experiments are the key, but experiments have to merge or fit with theoretical data. And in a way, if we understand one process, we get to understand the other one, and vice versa. Okay. Thanks a lot. Any question, just,
Thank you. So, as Nelson said, if there are any questions. Yes, please.
In your experimental setup, there are droplets that carry a single protein molecules that fly through this, or are they like microscopic number?
Yes. So what happened in terms of this? And let me show you the slide first. I don't know if this one is better or I think it's the same. This one is the same like this one. So this is time. So this is time zero. Time zero is a droplet, a big droplet, with a lot of proteins in there. As long as the collisions inside here, which are different collisions that I said, it's different collisions, and the voltage is quite high, this droplet is starting to separate. So there is a tendency to separate at the end with one single droplet containing one single protein. So the last stage before getting charged, which is like this one, you can see in most of the cases one single protein charged. So I don't know if I understand, but at the end, just prior to enter the instrument, you get one single droplet containing, in most of the cases, one single protein.
The ionization happens with proteins, or may happen with detergent as well?
Well, what we know is to get ionization, you need the solvent, because the solvent is the protein is getting the ionization from the solvent. So this is the water, the glass of water, and here you got the protein, right? So at the end, the water is getting removed, desolvated, but when it's getting desolvated, the proton from the water is getting attached to the protein. So that's how the charge coming from. So at the end, you got the protein plus protons coming from the water. That's a sample that enters the instrument, like a charged protein.
Thank you.
That's a sample.
Well, are there further questions? Well, we have time, please, around.
Yes, can you explain a little more your what you call the nanomechanical simulation?
Okay, so unfortunately I made a lot of videos, but I didn't make a video of the collision event, basically here. I'm sorry, I think this video is better than the video I show you here. Give me 1 second. This was one of our first videos, but we didn't pursue on that because it consumes a lot of computer power, so we cannot do that. But basically the same. We got a membrane protein, this one is a membrane protein, covered by the ring of detergent, and we built a tube inside the computer with the same dimensions that in the instrument. Of course, in proportion, the same dimensions of the protein. And after modeling the position of the detergent, we put the protein, for example, here, and we don't apply a voltage inside the instrument. What we say is we apply to the protein a kinetic energy. So in terms of the instrument, the kinetic energy is defined by the charge and the voltage. So we got the protein, which is charge, and instead of voltage, we said, okay, you are going to move at a defined kinetic energy. And anything that collides with you is going to reduce your kinetic energy. But that the system is going to give you that information, not yourself. You only define the first step, which is the kinetic energy. So the full thing is moving, go to the board. Here is covered by gas molecules. So if I'm moving quite quickly, I'm going to get the same number of collisions, but more energetic than if I move slower. What we have found so far in terms of the instrument, in terms of the simulation, is that if this collision event are more energetic, which means bigger gas molecules or a faster collision event with the protein, this detergent is destroyed earlier in the instrument. And it's basically the same interpretation that we got in the instrument. If we apply a bigger voltage in the instrument, the protein is removed from the detergent earlier. That's
So if I translate well, so your main system is the protein.
yes.
And well, you are working with an environment where you have the other particles better than colliding with the main system. Am I right?
Yeah, well, the initial system is the membrane protein surrounded by detergent. This is the sample. This is the key component.
Yeah.
And this is touching or colliding with the gas molecules inside a tube. So these molecules are, in terms of chemistry, these are noble gases. So if it's a noble gas, that moves like a Brownian motion. So it moves randomly.
Okay.
So in here, you don't see the random movement, but the gas molecules are moving randomly.
Yeah.
But the protein is moving just to the wall because I'm saying protein moves in that direction because you are charged in that defined charge state and to a defined kinetic energy.
Yeah.
So the only thing that is moved in that direction is the protein. The other gas molecules are floating around, and this collision event with the protein makes or trigger the release of the detergent.
Yeah. Okay. Now I understand, because it was not clear to me. Say the way in which the other particles were colliding with the.
Well, they're
protein.
colliding.
So
because the protein is approaching to them.
Yeah.
And that's basically.
Of course. So you have a given dynamics for that is for the protein, yes. And the other ones are simply random.
Right. And you can see here
Brownian motion particles.
Yes. And of course, this Brownian motion is affected because of the collision. Because can you see this small white is jumping around a lot because it's like a truck collided with a small car. The small car it's moved away.
The difference with the molecular dynamics simulation, in the other one, you put say Hamiltonian for
that's true. That's true. In terms of getting
huge Hamiltonian.
Yes. In here there's no Hamiltonian. It's basically Newtonian number 1.0.
Of course.
Action reaction. That's the only thing.
Yeah.
But the important thing for us is that with this similarity, we can extrapolate that, or we can infer that in the gas phase, actually, not a lot of reorganization in terms of chemistry. It's just collision between one thing and another.
And from the point of view of the computer performance, this one, you call that the mechanical.
Well, I call it nanomechanical because I like the name. But mechanical is because it's Newton plus 1.0, and nano because it's small. That's the only. Like,
well, we should call that probably stochastic dynamics, or open system approach.
If it's better for you, it's better for me.
But then that proves that you save money with this.
Yeah, that's all. It proves that this mechanism,
kind of
in terms of dynamic, in terms of the simulation, simpler. Can you get information from that? That's good. Okay.
Thank you.
Thank you. Are there other questions? Well, if not, let's thank the speaker again. And
thank you.
Well,